Yes, sir.
Okay. So today class day 23. Class day, is it 23?
Yes, sir.
Yes, 23. So what we discussed yesterday about the transformer vector group selection. This is what we started yesterday, right? Vector group selection. And we have taken the three cases that if in case we are working for any thermal power plant and we have the rotating generators, so what is the vector group we use in those kind of the power plant, and what is the conclusion what we will use? What is the conclusion? Suppose here we have the generator which is connected with a generator step up transformer, right? So what should be the vector group of this transformer, of this generator transformer?
GT side is the delta connected and the another side is the star connected, sir.
So HV side, this side should be star connected. So I write here Y, and there should be neutral. So I'm taking N. This neutral is coming out, so I'm putting N. Right?
Yes.
This neutral we connect.
Yes, sir.
This neutral grounding we do through a
NGR.
grounding resistors, NGR. Through that we
Yes.
do. So we have discussed that why we are using the NGR.
Yes, sir.
Why we use the NGR?
Due to the short circuit current, control to the short circuit current, sir.
To limit the fault current.
Yeah. So actually, in the generator we have the rotating cores. Let me come back. Just a 2-minute review what we have discussed yesterday. So coming back to the like power plant. So we discussed that why we take the NGR. Here we have discussed about the NGR. So HV side vector group neutral point should be connected to ground with a high resistance grounding system, and for that the neutral grounding resistor used in order to ensure that if any ground fault occur, NGR will not allow to flow high ground fault current towards the mother ground, as the power generation source is very much close, and this line to ground fault current will be much high, and this NGR protecting the generator against the high ground fault current. And the point that we have discussed, that the main goal of grounding through the NGR is to achieve the safety of equipment from the line to ground fault by limiting the ground fault current. And then again we have discussed about the for the this
Calculation NGR.
Yeah, here we have discussed that rotating machines, this is the important point. The rotating machines have very less withstand capacity for zero sequence fault current. Therefore, transform delta current is preferred at the generator side to stop the sequence current entering the generator, because the rotating machines have very less withstand capacity for zero sequence fault current. And if this zero sequence current enters the generator, then the generator core, this is the important topic. Let me core, this is important here. Core may come under saturation conditions quickly, and we cannot use the generator at site, and it needs very heavy maintenance, which will not be possible at site. So in order to protect the core, in order to protect the generator core by limiting this line to ground fault current, we are using here NGR. So NGR basically limiting the line to ground fault current, but why they are limiting this? Because they wanted to protect the generator core against high amount of line to ground fault current. So whenever we have the any transformer which is connected to the generator is a rotating equipment, so we have to put the NGR. I'm taking the same example. Let me cover on the same example. Let me cover other things. So what we discuss in case of if we have solar power plant, in that case, what the vector group we use, and we discussed that in solar power plant we have again two kind of the transformer. One is the inverter duty transformer, and second is the power transformer. So in case of the inverter duty transformer, we have discussed what is the vector group we selected. We select, right? That yesterday we discussed. And in case of the power transformer, also what we discussed that what is the vector group we select for the power transformer. Correct now. This is what we have discussed yesterday. And then after we discuss about the advantage and disadvantage of advantage of the graded insulations. Advantage of the graded insulations on the star connections. And by covering this advantage of graded insulations, we move on the when we have any EHV substation. So in that EHV substation, why we use the star? Why we used Y and Y and a 0T11? Why we use the vector group star here? And in order to add the advantage of the delta, we are putting the tertiary winding into delta connection. So about the tertiary winding also we discussed that why we use the tertiary winding. Why we use the tertiary winding? Is tertiary winding is mandatory that we discuss, and then we discuss that what could be the rating of this tertiary winding. This is what the study we have discussed. Now taking one more example, single and diagram study that I was putting. I think I have that SLD. Just give me 1 second. One SLD. So this SLD is for the NALCO, National Aluminium Company Limited. EIL is the consultant who have approved this. EIL is the consultant for this NALCO, and here we have a single line diagram. This is a HT2LT, like 11 kV switchboard. 11 kV switchboard. Here we have taking supply. Taking supply 630 ampere VCB. So 2005 ampere CT, 15 VA class 5P10. This is we are taking incomer from the state electricity board for this NALCO project. And then here we have 11 kV bus bar, 630 ampere, 3-phase. Generally, this bus bar rating we take equal to the incomer rating. So 630 ampere VCB, so 630 ampere bus bar rating here we have to take. 40 kilo per 1 second, 3-phase bus bar. Right here that we are using. Now here we have different feeders. So this feeder 1, feeder 2, feeder 3. Here we are using 400 ampere VCB, lowest rating of the VCB, 400 ampere. Then CT, and from here we are taking the feeder, and then this feeder we are feeding to a HT board. Here HT board, and this HT board is 6.6 kV switchboard. 6.6 kV switchboard. And from this 6.6 kV switchboard, we are taking outgoing feeder, which is feeding to the motors. Now we have motor here, 300 kilowatt intake well, motor working, spare motor, intake well, motor, standby motor. So like spare, standby, continuous motors here we are using. And that motor is high voltage motor, 6.6 kV motors. So in order to step down the voltage from 33 kV to 6.6 kV, we are using a transformer here, which is 2.5 ampere transformer, right? So 300 kilowatt this one, and I have 300 kilowatt this one as well. So 1000 kilowatt or 1 megawatt is the total load, but they are using 2.5 MVA, which is very much high in the size. Might be they have some future planning to connect the load. So now the point is that if we see this transformer, this transformer feeding to a bus bar, on that bus bar there is a direct motor connection. So now what we are doing here in this case, on this transformer, this arrow is wrong. This arrow should not be here because this is a small transformer. So OLTC is not required. So this arrow, do not consider this arrow, right? So now this delta star transformer here we are using like T by N11 like that. So if you see on the star side, we have done this NGR grounding, right? 12.7 ohm NGR we have taken. So why we have taken this NGR over here? Because this transformer is connecting to bus bar and they are feeding to the motor. So transformer is very much close to the motor. So in order to protect again the motor core, here we are putting the NGR. Or here this particular company who have prepared this single line diagram, they are putting the NGR. The same concept we can relate with the generator NGR over here. I'm taking different examples just to let you know that this is statement what I'm telling, that when we are the rotating machines, their core short circuit resistant capacity is very much less. They may come under saturation state quickly. So we cannot, like we want to limit the zero sequence current, or in simple language line to ground fault current, as much as possible. We want to minimize this. So due to that reason, in this particular project, they have used the NCR over here. Coming to this another switchboard, here if we come. So this switchboard is like, again, they are using the transformer. They are stepped down 33 kV to 400 voltage now. And now they are feeding to a 400 voltage switchboard. In this switchboard, we have like pump, small pump, sub distribution ports, cathodic protections, battery charger, spare. So there is no need big motor connected. There is no need big motor connected like 300, 400, 500 kilowatt to this transformer side. So here, if you see, they have used the solid grounding. So here solid grounding, and here they have used the NGRs. Am I clear with the generator, transformer, NGR? The same concept carry out with another project here, transformer, but in case of generator, we have the motor, which is also a rotating equipment. This is some comment on this facility, means cable size need to indicate. So,
Sir?
yeah.
One question, sir.
Could we discuss
May I
it?
ask?
Yeah, tell me.
Hello.
Yeah, tell me. Okay,
May I?
tell me quickly. Yeah, tell me quickly. Hello.
Yes, sir. Yes, sir. May I ask, sir?
Yeah, tell me.
Sir, for using of NGR, is there any specific rating of motor that means above this capacity we have to use NGR,
No,
or
there is no
it with this
see,
can be used anywhere?
see, if your motor capacity is like 300, 400 kilowatt, 500 kilowatt, so those motor are costly motors.
Okay.
Okay, and this is HD motors. This, if you refer this is HD motors
Yes,
here.
sir. Yes,
So
sir. Yes, sir.
we want to protect those motors.
Okay.
And this is a critical applications as well. So
Okay.
due to that reason, spares and standby they have taken here. So due to that reason, in order, since this is HD motors, critical motors, putting the NGR over here. Generally when we connect any transformer to bus bar, and if any like 200, 300 kilowatt motor come, we try to put the NGR here.
Okay, sir. Okay.
Yeah.
Thank you, sir.
Okay. So tertiary voltage rating that we have discussed yesterday, tertiary voltage rating and tertiary power rating we have discussed yesterday for the auto transformer. So large system tie-up transformer advantage and disadvantage. I think this is what we have discussed and studied up to this point. The tertiary winding, what should be their voltage rating and what should be the power rating. Right?
Yes, sir.
Now,
Power grid selection also.
yeah. Now coming, let us discuss about the when we are using a ICT or when we are using a auto transformer, when HT and like HV and LV is directly electrical connected. So what is the advantage and what is the disadvantage of the auto transformer? And since auto transformer is providing a huge cost saving, auto transformer is providing a huge cost saving because there is one winding in that. So why we do not use auto transformer is in everywhere? Why we are not using auto transformer everywhere? Like why we are not using auto transformer? Are not everywhere it is not used. So because they have some disadvantage as well. So just a quick overview. The auto transformer is a transformer with one common winding for the primary and secondary are actually in LV, both are wound on a common core. So therefore such auto transformer provide savings on the cost of copper winding material. Yes, because winding we are taking tappings. So when we are taking the tapping, in that case, another winding not required. So providing saving on the cost of the copper winding material. And since there is one winding, so losses also reduced, losses less, and there is no any problem of the flux linkers. There is no any leakage flux. All the flux is directly electrically connected. So flux linkage is better since there is just one winding. It is also smaller in size compared with the normal transformer. So this is the advantage of the auto transformer, but there is some disadvantage of the auto transformer as well. So advantage, it is less costly because my winding removed, copper, less copper required, so less costly. Better regulations due to single winding link HV and LV side, HV and IV side, we can say. So better regulations, low losses compared to the ordinary two winding transformer of the same rating. So losses is also lower. Now, but they have a serious disadvantage. The disadvantage is that there are various advantages of the auto transfer, but at the same time, some major disadvantage. One reason the auto transfer is not widely used is that the secondary winding, secondary or IV or LV side is not insulated from the primary winding. Or LV side is not insulated from the HV side. Am I correct? The secondary winding, I can put here LV or IV, whatever you want. LV is not insulated. I can write here isolated, from the primary winding, or it would be better to write the HV side. So what is the issue in that if not isolated? So if an auto transformer is used to supply low voltage from a high voltage, means if I'm using a auto transformer 132 by 33 kV or 33 by 11 kV, in that if I'm using the auto transformer, if auto transformer is used to supply low voltage from a higher voltage, and there is a break in the secondary or LV winding, the full primary voltage comes across the secondary winding, which is dangerous to the operator and the equipment. So the auto transformer should not be used for interconnecting high voltage and low voltage system. This is used only in limited place where a slight variations of the output voltage from the input voltage is required. The primary and secondary winding are not electrically insulated. Now one more problem we can list here, that whatever the fault current, the fault current, the fault current of the HV side, may come to the LV side as well, right?
Yes, sir. Yes, sir.
Fault current of HV side may come to the LV side as well. So this is also a disadvantage, that this auto transformer is not widely everywhere it is used. So whenever we have like voltage variations between HV and LV, when the voltage variations is less, in that case, this auto transformer is a better choice. Please mute. Yeah. So in that case, auto transfer is better choice. But if in case, yeah, yes, less than 2. If in case, if the variations is too much high, in that case, it is not allowed to use. And one more point you can see, from this auto transformer. Let me take the snapshot that whatever the disturbance harmonics, whatever coming to the load, if I'm using this transfer for the load purpose, so whatever this load is injecting the harmonics, the unbalance, like zero sequence current, that is directly coming on the HV side, and that is directly feeding towards the source, towards the grid as well, which is also not good, not desired. So due to that reason, again, this auto transformer we do not use for the industrial applications. We use, in that case, what we use two wound type transformer, right? Where HV winding and LV winding both are separate, isolated, only magnetically coupled, right? But if I use this transformer, in that case, whatever the load side harmonics, unbalance, zero sequence current, all the things will be feeded to here. So due to that reason, this kind of the transformer is used only in the grid system. It is only used in the grid system, where the HV side and LV side is not feeding to any kind of the load. They are not feeding any kind of the direct industrial load. It is the part of the grid system. So in those kind of the grid system, this kind of the transformer is can be used. It is used like, and like the regular standard practice when HV to LV voltage ratio is less than 2, then it is preferred to use. But it is not the IEC standard only. Few countries, like if I refer to any project in UK country, they have the voltage level like 400 kV, 270, 275 kV, 132 kV. So in 400 by 275 kV, obviously they will use the auto transformer. Right? In 275 kV by 132 kV, again, in that case, again, they use auto transformers. Even the voltage ratio is high, but they use auto transformers. And in few substations, they have 400 by 132 kV as well. 400 by 132 kV as well. What is our standard practice that we have established? The concept, regular concept, that HV to LV voltage ratio should be less than 2. But here my HV to LV voltage ratio is greater than 2. But again, those countries are using the auto transformer because the reason is that their 400 kV is the grid voltage, 132 kV is the grid voltage. My 132 kV is not directly feeding to any kind of the industrial load. They have another 33 kV, through that they feed to the industrial loads, right? So whenever they have any grid substations, any substations which is a part of the grid, in that substations, for 400 by 132 kV also, they use the auto transformer. They are utilizing the advantage the auto transformer, because their 132 kV side is the part of the grid and not connected to any kind of the industrial load which can inject the harmonics or unbalance into the grid, right? I hope I'm clear about that. What is the disadvantage of the auto transformer and what is the advantage of the auto transformer, and why the auto transformer cannot be used everywhere in the electrical system. Now coming to the another kind of the applications. So here we have discussed thermal power plant, solar power plant, extra high voltage substations, right? And now when we have any distribution substations, by 33 by 11 kV, that I think here we have discussed that what we use P by N11. So, and if there is, we have any distributions, pole mounted substations, means there is two are 4-pole. On the 4-pole, we are mounting the distributions transformer that could be 100 kV or 200 kV transformer, just taking 11 kV or 33 kV from the distribution substations, step down it to 400 voltage, and from this 400 voltage again feeding to the end load, to the consumer. So in that case, what is the vector group we use and why that vector group we use? Let us see that. Well, so normally the dy and NY vector group is used in the distribution system transformer. The first reason is that LV side star point facilitate mixed loading of three-phase and single-phase consumer connections and industrial loads. So here they are telling that they will use the D, first of D they will use, then they use the Y and then 11. So this is star they are telling, because here we have the star, here we have the star, so here we have the neutral also. So here we have the three-phase four-wire system, three-phase four-wire system. So RYB phase and then neutral also. So here we have the choice that whether we can feed the three-phase load or we can face the single-phase load as well. So like RYB and then neutral. So single-phase load also we can feed here. So it provides this facility by using the star and single-phase consumers. The second reason is that in industry, the maximum load is of the non-linear type and they generate harmonics. So this effect we do not want to reflect in the primary grid side, and due to this reason we use delta on the primary side. So non-linear loads may be, for example, furnace, heaters, VFD, these type of the load called as the non-linear load. And these non-linear loads generate the harmonics in the system. For that we use dy and 11 vector configurations in the transformer. So whatever harmonics of LV voltage coming from the industry will not be sent in the piston system due to the delta winding in the HV winding or HV side. The third reason is that whenever a single line to ground fault occur at LV side of the transformer, the reflected single line to ground fault current at the HV side does not have the zero sequence fault current contributions. So here we can see we have delta and star transformer and single line to ground fault current if fault happening this side. So here if we see at the HV side, we have 697 and 698 ampere current. So this single line to ground fault current convert into line to line fault current. We can establish one simulations as well. Zero sequence current occurred LV side of the transformer. This reflected single line to ground fault current at HV side does not have the zero sequence fault contributions value. So on the HV side of its delta connections, the zero sequence component will not be reflected at the HV side. It will only circulate within the winding and not come outside of the delta connected winding. HV side of the transformer is unaffected by single line to ground fault, only able to see positive and negative sequence component are reflected. So only positive and negative sequence component reflected when single line to ground fault occurred at LV, and HV system protected are unaffected by single line to ground fault current. So due to the above reason, the LV side star connected and HV side delta connected winding configuration is preferred in case of the distributions system. Let us see some advantage and disadvantage again to conclude. So LV side in a star converting three-phase three-wire system into three-phase four-wire system. This is one advantage of a star. Star connections provide the neutral point for the LV side, so possible single phase loading. This is advantage of a star. HV side in delta. So when unbalanced at LV side, the same unbalanced current does not come on the HV side system. They use delta as the HV side suppress the unbalanced current and HV system remains stable. So providing the balance. The effect of LV side single line to ground fault not coming on the HV side. The third or multiple of third harmonics present at LV side has not come on the HV side. So due to delta winding in HV side upstream system. So these are some advantage and disadvantage of the star and delta, and that we are utilizing in selecting the transformer vector configurations. So let us see some physical or practical cases when we have a electrical system and we have a transformer, existing transformer, suppose dy-n1, and we are adding one more transformer. If in case both transformer need to run on the parallel, so HV side on the same bus, LV side on the same bus, same source we have, they need to run on the parallel. We are taking both the same identical vector group, and LV side there is no any load connected. So you can see in this uh, snapshot of ETAP, there is no any current flowing, 0 kVA, 0 and 0, everywhere it is 0 because there is no any load connected here. So let us take a case where in the industry we have 2 into 100% system design, or after 3 to 4 years, if the load increased and power demand increased and we need to connect one additional transformer, and we have to run two transformer in parallel operations. In this case, both transformers must have the same vector configurations. So let us take the case in ETAP. If we run two transformer in parallel, so this case, this would be the case. Let us take this exercise with ETAP as well. So now we have a source. Source is 1110 kV. I'm not source different over here. The source, from the source we are taking supply connecting to a PCC or HT panel, which is 1110 kV by in this case, particular case, and connecting to transformer. So here we have one transformer. This rating is 1110 by 11 kV, and suppose it is 30 MVA, right? And impedance is and everything are putting the same delta I star, and again it is delta 110 by 11 kV going to the grounding, and then delta I star solid. And here if we check, this is grounding, delta I star solid. And now if we run the load flow, let us see if both is identical vector configurations. Both here, no, this vector configuration is not identical. Here if we check grounding. So here we have used dy-n1, right? dy-n1 angle 30 degree. HV leads LV. That's fine because they are leading HV. This is okay right now. HV leads LV. Is that fine?
Yes, sir.
Minus 30. So dy-n11. Now at there here ETAP is taking some different. HV leads LV. Now they are minus 30 angle. So running both in the parallel. Yeah. So when we have two identical vector configurations, dy-n11 and dy-n11, in that case, 0 ampere and nothing, everywhere it is 0. Now, if by the chance, if we have a different vector group, now we are changing the vector group from dy-n11 to dy-n1. In that case, both have the different vector configurations. It is dy-n1, it is dy-n11. In that case, if we perform the power flow or load flow analysis, let us see. There is no any load connected here. Ideally, there should not be any current flow, which is we have seen in the previous case. There was no 0 ampere current flow. But again,
Yes, sir.
here the current is flowing, which is 630 ampere current is flowing. Current is flowing. And here if you see, current coming from source to here, dy-n11, coming to the bus bar and then going back to the transformer. So now, in this particular case, even though this is a transformer, but this transformer is a source, but in this particular case, this is working as a load and this transformer. Isn't it?
Yes, sir.
Okay, sir.
So due to this reason, practically when we take two transformer in the parallel conditions, we say that both transformer rating, impedance, then vector configurations must be identical. Our vector configurations, if you see here, it should be identical. If dy_n1, dy_n11, now without any load, this transformer is overloaded. So due to this reason, we used to say that whenever two transformers running into the parallel, both transformer must have the identical vector connections or vector configurations. So whenever you perform the this study, there is one point here that need to be take care. Go to the load flow study case and click on the apply transformer phase shift. If you will not apply this, click on this. So this study will not give this result. So during this, need to click on this apply transformer phase shift and then perform the study. If you see, I have taken two different conditions, right? But why not?
Yes, sir.
Why not happening anything? Because I have not selected this. So apply transformer phase shift. Click on this, click OK, and then run. Then result is coming out. Okay. So this is the case. This is the case for the that both transform must have the identical vector group. Otherwise, one transform will work as a load on the second transformer. Let us see what is some project extract for the vector group. So this is 500 MVA, 400 by 220 by 33 kV. So actually, how much? 500 MVA, 400, 500 MVA LV, 220 kV, and 33 kV. How much? We have discussed that we design 1/3. So 500
Yes.
MVA
Yes, sir.
into 1/3, which is 166 MVA, which is here. Voltage here.
Yes, sir.
Vector configurations here that we have discussed. About cooling we will discuss, right? And then for 200 MVA, 220 by 132 kV. Again, we are taking YN0 D11 and 80 MVA. So 130 by 33 kV. Huge difference in HV and LV voltage. So we have to take
Yes, sir.
two winding, and which is YN0 we are taking here. Let us take. This is as per the Indian engineering practices. Let us see what we select in the UK. So I have taken a snapshot of the UK national grid, their voltage and their transformer vector configurations. So for any 400 kV by 275 kV or any 275 400 by 132 kV or 275 by 132 kV. So here they take the YN0.
Yes, sir.
Both sides they are taking the star. Both sides they are taking the star at 132 kV. So here is star. So there is no phase shift occurred here. So this RYB and this RYB, the phase displacement is 0 here. Now they have one voltage level, another voltage level is 132 by 33 kV. And in the 132 by 33 kV, they take delta on 33 kV side. This is what their usual practice. Delta on 33 kV side. In our case, what we take? In India, what we take?
Delta on the HV side, sir.
So in India, it is reverse. This is matching as per the Indian practice, but here 130 by 33 kV. So generally we take D, Y, and 11, but they are taking Y.
Yes.
Here, D here, delta here. Since they have delta, due to that reason, they have to use the earthing transformer or zigzag transformer, which is here. Zigzag transformer. And now this zigzag transformer, they are grounding with help of the neutral grounding resistor.
NG.
Here. So this delta they are using here. Earthing transformer they are using here. I'll come on the earthing transformer in the earthing module, I will discuss this.
ఓ అల్లా అది పేరు చాలా మంది పోరా என்ன பண்ணது
Ghazi Muhammad, mute yourself. Yeah. So I'll take this topic in the earthing module about all these combinations. Why D1 here? 130 by 33 kV, since they have used the delta here, delta here, so it's coming, and one vector group. About this vector group, I will again check and then confirm. So please do not focus on this. I will again check in what approach I have written this vector configurations, how we have rotated this. I will double check this. Okay, and now they have another voltage range which is 33 by 11 kV. In that case, in that voltage range, they use dy11 again, dy, and it will come because they are taking out, so dy and 11. Here again, y and d1 means they are not indicating about the neutral, they are just telling about the HV and vector configurations. Due to that reason, n is not coming in this complete snapshot. So dy about the vector configurations only we discuss. So dy and 11 again. So if you see this 11 and if you see this vector configuration, so how much shift we have done? How much, like earlier it was on 1 o'clock. This is my HV voltage. This is my LV voltage, right? So now this 1 o'clock have to 11. 11 means my LV leads 30 degree to HV or by HV. So now I'm rotating 30 degrees. So this one will reach on the 12. Here they have 9 o'clock. So this will come on the 8 o'clock. So because entire we have to rotate on 30 degree. And similarly, this will again rotate. Means it might be at 6 o'clock. So it is coming on 5 o'clock like that. So 11 kV by 400 voltage, they have another voltage level in their country. And for that, again, they use dy11. This is what the UK grid or entire electrical network vector configurations they used to follow. Okay. Now I hope that this vectors selections, this parameters is okay for all of you. Please let me know if it's okay. We can move to the next parameter. So taking the transformer, we have listed out what is the parameters for the transformer selections and sizing. What was the parameters that we have listed in the beginning? Yeah, so transfer type are number of winding symbols, 3-phase transformer, 3 single-phase transformer bank, MVA vector group. This all we have discussed. Now coming off the type of the cooling selections. So from point 1 to point 4, am I clear on all the point 1 to 4?
Yes, sir. Clear.
So now coming to the next parameter for the transformer selections, which is about the cooling selection, and this cooling depend on the MVA rating. So based on that, we will discuss about the cooling, and along with the cooling, we will discuss about the losses as well. And taking the concept of the losses, we will discuss about the transformer rating, and we will discuss about the transformer derating as well. So a lot of things we have I have combined here for the transformer cooling. So first, let us start with the fifth parameters, which is transformer losses, and then WTI, winding temperature indicator, oil temperature indicators, OTI, and cooling of transformer. After that, we will reach on the cooling of the transformer. So let us start with the losses first. And this losses converting into heat. Due to that reason, we have to use the cooling in the transformer. So let us see what is the type of the losses we have in the transformer. So why losses is occurring, when the high current passes through the transformer winding, then the losses start occurring in transformer winding, because winding have some impedance, current is flowing, so I square into R, there would be there would be losses in the winding and core as well. So below is some brief summary of the transformer losses type. So summary of losses: power losses, uh, that could be there could be three type of the losses in the transformer. One is the no load losses, second is load losses, third is auxiliary losses. So no load loss means transformer is not connected on the load. If we just connect the transformer with the supply, there is no any load running, but again there would be loss in the load in the transformer. So those losses we are referring as a no load losses, and those losses would be our hysteresis losses and the ED current losses. And when transformer is connected with the load, full load coming on the transformer, in that case, the losses which is occurring in the winding, like I square into R, ED in winding and stray in metal, these comes under the transformer full load or load loss. Third type of the loss we have, which is called as the auxiliary losses. Auxiliary losses means if you see here, let me take a transformer photo. Here, if you see, we have the transformer, we have the tank, and we have the radiators here. In the radiator, we have placed the fan. So this fan have the motor, which is forcing air into the radiator. So this motor required some power. So this motor power we are covering are taking under transformer auxiliary losses. So that we are putting here transformer auxiliary losses due to cooling motor and pump, the fan motor and the oil pump. So those losses comes under the auxiliary losses of the transformer. Let us taking this losses concept, let us see about the transformer ratings. A very interesting concept about the transformer rating. Let me ask you, let me directly tell you what is the point, what I'm trying to tell. So to explain my concept, I have taken the help of the IEC 60076 part number 1. Clause number 3.4.6. What is this clause telling of the IEC 60076? This is rated power as R. So IEC defining the transformer rated power, any power like 2 MVA, 3 MVA, 4 MVA, whatever we are taking. So this IEC is defining a conventional value of apparent power assigned to a winding, which together with the rated voltage of the winding determine its rated current. Both winding of a two-winding transformer have the same rated power, which by definition is the rated power of the whole transformer. So they are telling that like the voltage and which determining the current and apparent power, that should be rated power of the transformer. It means when we say any specific rating of a transformer, for example 4 MVA or 2 MVA or 3 MVA, whatever, so this 4 MVA is the total rating of the transformer considering all the losses occurring in the transformer. Losses is what we have discussed about the losses. This losses. So this means that on a 4 MVA transformer, we cannot connect the 4 MVA load, as there are losses also occurring inside a transformer. In industrial practice, sometimes we used to hear that we should do 80% or 85% loading of the transformer. So I think we can relate this loading also. So we also used to hear that about 80% of the loading should be connected to the transformer. This concept is only for the transformer, not for any other electrical equipment. Let us see any example as well. Means if we take, let us take an example. So here we have a source then we have bus, then transformer, then again bus, and then some load we are taking. Let us take some load as well, right? So taking this 6.6 kV, connecting this source to this bus, connecting this to this transformer over here, taking the bus here, taking a lump load connecting to here. Now let us take this is a 33 by 11 kV or a 11 kV 400 only. So let us take this is a 11 kV. Our general practice 11 kV bus bar, and my source is also 11 kV, right? Transformer, let us take any 4 MVA transformer then, and here 0.4 secondary voltage. Let us take any 4 MVA small transformer only. Let us take the impedance, typical impedance. I'll come on the impedance as well. LV side we have the 0.4. Then let us take this 0.433 like that. And lump load here, let us take a lump load. Now I'm taking the full load. I'm taking 4 MVA transfer, so I'm taking full 4 MVA load. Let us take 100% this load. And then let us see what is current is flowing. So let us take a 4 MVA load. 4 MVA load. For MVA load, lump load. So I'm putting 4 MVA taco, 4 MVA load. And if we perform the power flow study, lump load rated kV is out of lump 7. This is what should be the rating of this 0.4, right? And then again performing load flow. And let us see the power now. So I'm taking megawatt and JM. Putting here. Could we see here what is my see this transformer, and I'm putting the like alert maximum. I'm putting now 4 MVA alert here, right? So if we see here this transformer, how much loading on the HV side?
4.3.
4.3, right?
Yes.
4.3. I'm connecting a 4 MVA load, 4 MVA load, and the rating coming on the HV side, this is 4.3 MVA. It means, and IEC is defining that the HV and LV both should be 4 MVA. Means in this case, if I connect the 100% load, my transformer would be overloaded. Why it is happening? Why it is overloaded? When we say in specific rating of a transformer 4 MVA, so this 4 MVA is the total rating of transformer considering all the losses. So I'm putting 4 MVA load plus losses also happening. So total requirement or total load on the HV side winding is now 4 plus losses, which is 4.3 MVA. Am I making sense? I'm just taking the example of the IEC what telling, and I'm trying to make it easy of the IEC example. So class IC 60076 class 3.4.6 also define the rated power as the total apparent power. So this is case only for the transformer. Except the transformer, if I take the motor, in that case, this is not the case. If I'm telling 4 kilowatt motor or 4 megawatt or 400 kilowatt motor, it means, for example, if we take a 4 kilowatt motor, it means the 4 kilowatt is the mechanical output power of the motor. 4 kilowatt is the mechanical output. The electrical input of the motor would be higher than 4 kilowatt. Power of the motor is 4 kilowatt, and the electrical input of the motor will be higher than 4 kilowatt. It may be 5-6 kilowatt, like that, due to the losses of the motor. The same concept we have written here. 4 MVA 33 by 11 kV we have taken in this example. So now 33 by 11 kV, when I'm putting a 4 MVA transformer, 4 MVA load. So this transformer is like red, 4.2 MVA they are taking from the grid. And once it is overloaded here, once I took, and red is indicating the overload alert here. So if I'm taking a transformer, 4 MVA transformer, connecting a 3.5 MVA load just on this transformer. So they are taking 3.65 MVA, which is lower than the 4 MVA primary side. And there is no any alarm overloading alert coming here. Am I clear? What we discussed, what is the concept that we established? What the concept that we established in case of the transformer and motor? In case of the transformer, if I'm telling a 4 MVA transformer, so this 4 MVA is the HV and 4 MVA is the LV as well. Only what is changing? What is changing? The voltage, right now. The voltage
Yes.
changing.
Yes.
When the voltage changing, accordingly current is changing, right? Frequency also a potential.
Yes.
So this should be loaded based on 4 MVA, and this should be loaded again based on the 4 MVA. So if I connect the 100% load on this transformer, 100% load if I'm connecting on this transformer, in that case, my LV side is 4 MVA loaded, but my HV side is loaded as 4.2 MVA, which is overloading of this transformer. And we used to hear in the industry that we should do 80 or 85% of the loading as well in case of the transformer. When I take this concept is applicable for the transformer only. If I'm taking any other electrical equipment, suppose I'm taking motor. So if I'm taking 4 kilowatt, so this 4 kilowatt is what? Whether this 4 kilowatt is the input power. 4 kilowatt. If I'm telling a 4 kilowatt, I have a 4 kilowatt motor. So what mean by the 4 kilowatt? Is it the 4 kilowatt is input power or it is the output power? Output power. So the reply is that 4 kilowatt is the mechanical output power of the motor. The electrical input power would be higher than 4 kilowatt. So due to that reason, if you are selecting any starter, any VFD for 4 kilowatt, do not select the 4 kilowatt of the starter or the VFD. Try to take at least, if you have 4 kilowatt motor, try to take 7.5 HP VFD. VFD means 5.5 kilowatt VFD. Right. Similarly, the starter and soft starter or dual starter, whatever you are taking. I hope I am clear with the losses, which is the main topic. Losses. Taking the losses, I have explained about the rating and then loading of the equipment. One more example here. This is derating. So any transformer, their power 4 MVA or 5 MVA, this power is defined on a certain, let us take this, on a certain installation's altitude and ambient temperature. Generally, the transformer is designed for the installation's altitude below 1000 meter or till 1000 meter above mean sea level. If my installation's altitude is increasing from 1000 meter, it is further increase 100 meters. So every 100 meter, provide 2% derating in the transformer output. So it means a 4 MVA transformer can be loaded over up to 3.9 MVA only. There is 2% derating occurs in the transformer. This is point number one. So this is also important. When you are review the any transformer GTP, you also make sure that what is the installation height mentioned. Particularly when you are working for any hilly substations. In that case, this parameter is important. And the transformer is designed on a specific site ambient temperature. In general practice, if we take any like Indian project or Asian project, generally it is designed based on the 50 degrees Celsius ambient temperature. Unfortunately, in ETAP, we do not have 50 degrees Celsius options. The ETAP, this is a drawback of the ETAP. ETAP tells only 30 degrees Celsius temperature, right? But transfer is designed based on the 50 degrees Celsius temperature. If you see 30 here, so no need derating here. But if I'm taking 50 here, so there is derating. Means 4 MVA, I can load only 3 MVA only here. And 80% is derated. Means every 1 degree Celsius temperature providing 1% derating in the transformer output power. This is a drawback of the ETAP. ETAP have taken ambient temperature 30 degrees Celsius. That should be taken as 50 degrees Celsius, right? Okay, so whenever we do any kind of the study through ETAP, even though your site temperature is 50 degrees Celsius, but in ETAP we put 30 degrees Celsius. Okay, so that derating we can avoid. And based on this will be based on the 4 MVA only. I hope I'm clear about both concept. So this we have discussed. Coming to the next. So the transformer rating is designed with an installation height of less than 1000 meter above the sea level or mean sea level and specific site temperature. When the installation height increase above 1000 meter, the transformer rating start decreasing, derating. Generally, each 100 meter above 1000 meter gives 2% derating in the transformer rating. Generally, the transformer rating is designed at an ambient temperature of 50 degrees Celsius. So when the temperature increases above 50 degrees Celsius, the transformer start derating. Generally, 1% derating occurs at every 1 degree Celsius temperature rise. So make sure when you review the GTP of transformer, make sure what is the rating, and that rating is corresponding to what site temperature. This is important. If your vendor sometimes written site temperature is 40 or 45 degrees Celsius, so ask him to provide the rating based on your ambient temperature. Generally that will take 50 degrees Celsius, so you ask him to take exact site specific temperature. Hope I am clear on two, three concepts we discuss all together in combinations. What we discuss, let us add this. What we discuss, let us summarize this. We discuss about the what kind of the losses occur in the transformer, right? Then we discuss about that whatever rating I am telling, this is rating of HV and rating of HV and LV. Means if I am telling you 4 MVA transformer, it means 4 MVA is my LV power and 4 MVA is my HV power, right? And this transformer cannot be connected with the 4 MVA or 4 megawatt or 4 MVA load. The reason why it could not connected, I hope that we discuss and it is clear. Then what we discussed, third point, that transformer design based on a specific site installation height and a specific site temperature. So if my temperature and installation height increasing, transfer start derating. So during the transfer GTP review, we need to make sure that what is the installation height and temperatures is written by the transformer manufacturers. Now coming to the fourth next point, that when this losses occurring in the transformer, This losses is generating the heat inside the transformer, and that heat will come on the transformer winding. And once the heat coming on the transformer winding, then winding loading capacity will decrease. So due to that reason, we have to provide the cooling, and we have to sense, or we have to measure what is my temperature increase inside the transformer. So these transformer losses converted into heat. Heat is I square into R, as we know. So current into resistance, heat, which increase the temperature of the transformer winding and core as well. So result in increasing the temperature of the transformer insulating oil heat will increase, as the oil is responsible for dissipating the heat, and oil is in touch with the core and binding, so oil temperature will increase. So for the safety of the transformer, we need to detect this heat in the transformer, and for this reason we use the WTI and OTI. So with help of the WTI, we are directly measuring the winding heat, right? Because your winding is the source of the major source of the heat, which is our winding is inside the winding losses occurring, and winding is the major source of the heat. So we are detecting the winding heat. But what will happen? The winding heat may not be everywhere uniform, may not everywhere uniform. So what we are doing this, in addition with the winding heat, we are also measuring the oil heat. What is the temperature increase of the oil as well? So WTI and OTI in the transformer we use, and WTI and OTI meter reading instrument are installed in the transformer marshalling box in the substation yard. Here I have taken the transformer marshalling box inside view, front view without door, means there is no door. Our door is opening of this marshalling box. In that case, we can see that there is meters. So WTI for the overall oil temperature measurement, and we have LV binding and we have HV binding. So due to that reason, we are using the LV WTI and HV WTI as well. So to WTI meter reading instrument are installed in the marshalling box to display the measurement of the top oil temperature and winding hot spot indication. And then this WTI OTI are wired cable connecting till wired till the transformer RTCC panel. RTCC panel, we are taking cable for remote indication of the same of temperature inside the control building, and we can see the wiring diagram as well. So like here we have local indications, but each and every time operator cannot come near to the transformer marshalling box, and each and every time operator cannot check what is the temperature going on the transformer. So due to that reason, we require a remote indication as well. So for the remote indications, we do the cabling in the transformer marshalling box, from the marshalling box to the RTCC panel. So I have taken a snapshot of the transformer vendor drawing. In that they have indicated the transformer time, transformer marshalling box, and then RTCC remote tap changer control panel, RTCC panel, which is used for the OLTC operations, right? Remote tap changer control cubicle like that, RTCC. So now if you see from the transformer tank, oil temperature sensing bulb with inbuilt PT. This is our transducer or instrument that detecting the temperature. So oil temperature, LV binding sensing bulb with inbuilt PT100. PT100 is the model of the RTD. RTD stands for the RTDVT for the temperature sensing, right? So we take RTD, PT100 is the RTD model, PT100. So LV WTI sensing bulb, and along with that we are putting the CT on the WTI, and from that also we are sensing the winding temperature through the current. And then we have HV WTI, and then HV phase WTI CT we are putting, and then from through this current also we are sensing the heat. And connecting to the transformer arsenal box here. So local air temperature indications OTI, they are indicating the oil temperature, winding temperatures, LV and HV winding temperatures, and from that temperature we are taking the output, we are taking the cables, and that cable we are connecting to the RTCC, and here we have the digital remote indication for the OTI and WTI as well. So that sensing we do. I hope I'm clear that why I'm doing this, why it is required. Now here we have the same thing, the same concept we apply into single line diagram as well. So with reference to above drawing, we can see that for the OTI and WTI, one are two thermo wall pockets. Here we have thermo wall pocket that inside tank manufacturer need to provide. So thermo wall pocket are provided on the transformer tank cover. They are typically 150 millimeter long, and in the pocket oil is filled, and a bulb with temperature sensing element like RTD, which is PT100 is the model of RTD, is inserted. RTD measurement is taken as top oil temperature. So this RTD is sensing the top oil temperatures. To get the winding temperature, the current proportional to the rated current of the transformer, this is important here, is passed through the standard resistance of WTI. The temperature rise due to I square into R represents the hot spot gradient for the selected R. The rated current could be 1 ampere, 1.6 or 2 ampere as per the manufacturer design, which produce the temperature corresponding to that desired gradient. So what I'm telling here, let me take the calculator, and then I have a 200 MVA transformer, right? This is the extract of the SLD. So 200 MVA converting into kVA 1000 and divide by 1.732, and then divide by, this is 220 by 132 kV, 220 kV, then HV side. So could you see here the current coming 524? So what should be my WTI city rating? What should be my WTI city rating? 600, right?
Yes, sir.
Make sure.
Yes, sir.
Make sure when you are doing review or making the SLD, you are taking the bushing CT. Here we have taken the two core in the bushing or turret CT. One we are using for the REF purpose. So this current rating we have taken equal to phase current rating, and neutral again we have taken equal to phase current rating, which is 1000 ampere. But my second CT will not be equal to 1000. Why? Because I need the current exact equal or near to my transformer current, because from this current I am sensing the temperature. So due to this reason, this current should be close to the transformer rating. So 524 is the current coming. So nearby standard rating is 600 ampere available. So we have taken 600 ampere for the WTI. Am I clear why I have taken 600 ampere here? Or what we should take? What we should take for the WTI CT? What the current we should take? So now this OTI and WTI indicate the instantaneous temperature of oil and winding of the transformer and record maximum temperature rise of oil and winding and operate high temperature alarm at a predetermined value of the allowable maximum temperature limit. So we have set the maximum temperature limit of the transformer. So if my sense our measured temperature is exceeding to allowable temperature limit of the transformer, then they will like start cooling system, or they can start the they can do the tripping as well. So alarm at the predetermined value of the allowable maximum temperature limit, trip the transformer filter circuit breaker when the temperature of the oil or winding reaches a predetermined maximum limit. So they have the capability to trip the transformer as well, to issue the trip command to the breaker as well. Control the cooling system of the transformer means we have the fan and pump. So those fan and pump is controlled by this OTI and WTI, and turn on the cooling equipment when the winding attains a preset high temperature, and turn it off when the temperature decreases by a set differential or set value. So let us see that. So as well, we have seen the transform. Before coming to the cooling, am I clear that why we use the WTI and OTI? Why we use the WTI and OCI? We discuss about the losses. The losses concept we extend till the rating of the transformer, and the rating of the transformer we extend that how much loading we can do on the transformer, and that we extend it what is the derating of the, about the derating of the transformer, and then this concept we extend that since losses occurring generating heat, so this heat should be sensed, and for that we are using the temperature indicators. And we have since that we have discussed that temperature is measured at locally in the Marcelin box and in the remote control remotely in the RTCC, which is placed inside the control building in that, and for that we have to do the wiring as well. And we discuss about the WTI, we take the CT for the WTI, and we discuss what should be the WTI CT rating. This is what we discuss, right? Am I clear so far? Am I clear so far about the uh, transformer, losses, ratings,
Yes, sir.
deratings, and the WTI and OTI? Now, since this WTI and OTI is controlling the cooling of the transformer, so let us discuss about the cooling of the transformer and what we do for the cooling for the transformer. So as well as we have seen that transformer losses are converted into heat, which increase the temperature of the winding, and core, which increase the temperature of transformer insulating oil. So in order to dissipate the heat generated in the transformer, additional cooling system, which is the radiator, attached to the main tank. So this radiator that we are attaching with the main tank, here we have the main tank. This radiator have a single work that it circulates the oil. It circulates the oil. So when oil circulates, it cooled. And dissipate the heat generated in the transformer, additional cooling system radiator attached to the main tank, and forced cooling system, like we can use the pump which will easily circulate the oil or forcibly circulate the oil, and in the radiator we can attach to the fan as well, which will forcefully force the uh, like air on the radiators, and that will help in cooling of the transformer. And forced cooling system, oil pump and cooling fan connected to the radiator would be required. So the force cooling equipment should come into operation by preset contacts in WTI, and the transformer will operate as a force cooled unit for use cooling method later symbols used in the transformer. So here if you see, we use this symbol like ONN, which is stand for the oil natural air. Nature means there is no any cooling force or separate cooling we are doing. Everything is naturally happened. At ONAF means oil is circulating naturally, but air we are forcing. So this is air force cooling, and OFAF means oil force and air both are we are forcing to the radiators. So what we do, as per the standards, we follow the symbol cooling medium. If mineral oil or equivalent flammable synthetic insulating oil liquid, in that case we use the O. If in case cooling medium is air, then we use A. So O stand for the oil, A stand for the air. Kind of the circulations. If the circulation is natural, then we use the N symbol. And if we are forcing, so in that case, we use the F symbol here. Right. So those symbols we indicate into the SLD as well. Let us see. Where which kind of the cooling we should select. So in case of the small transformer like 100 kVA, 200 kVA transformer, in those kind of the transformer, the ONAN type cooling is selected for a small rating transformer. For example, if the transformer rating is less than 10 MVA, till that rating ONAN type cooling can be selected. If I'm like taking another cooling, so what is the disadvantage? If I'm taking ONAF, OFAF, so what is the disadvantage of that cooling? What is the disadvantage of that cooling?
Losses.
Losses, auxiliary loss will be
Yeah.
increased.
Yes. In that case, my when I'm taking the pump, and when I'm taking the fan, which has the motor would be something like 1 HP or 0.5 HP motor. It means the auxiliary losses due to the fan and motor, this auxiliary losses coming into the picture. And when we are doing the force cooling, so what we are getting when we are transformer is cooled, in that case what we are getting the higher output, higher rating from the same transformer, right? When my transfer rating is small, like I'm taking a 100 kVA transformer, and when I'm putting the force cooling, my rating is increased, but at the same proportional, my losses will also increase. So there is no any net profit. There is no net advantage we are getting, even though we are getting some higher rating, but at the same time losses we are increasing. At the same time, the dimension of this transfer is also increasing. So in a small system, the ONAF or OFAF is not have any significant advantage. So in the small system, we go with the natural coolings. But when my transfer rating is in the MVA, like 60 MVA, 50 MVA, 100 MVA, in that case, when we go with the like cooling of ONAF, ONAF or OFAF, when we go the force cooling, in that case, my transformer output power is increased. Generally, it is increased by 25%. Let us see this, how much it is increased. So I'm taking the same transformer for MVA. Classes, here is the cooling. So I'm taking ONAN. So in the ONAN, like there is no any advantage I'm getting. But if I'm taking the ONAN and ONAF, now oil is naturally circulating, but air I'm forcing. In that case, how much the same transformer can deliver a 5 MVA load. Or 5 MVA load we can connect on that. It means transfer rating is increased. How much? It is around 25%,
25%.
right? So in the big rating of the transformer like 50, 60 MB, 100 MB, it is worthwhile to take the cooling, whether because this rating is increased, uh, transfer rating is increased, and only small amount of the losses, auxiliary losses is increasing, so that could be manageable. Similarly, if we go with second stage, I'm going ONA and ONAF and OFAF, then again we can see that 6.259 fan and pump both coming into the operations because taking oil force. So 6.25 here again 25% is this rating is increased. So in case of the small transformer, we go with the natural cooling. There is no any like significant uh, power increased when we increase the cooling. But in case of this large transformers, we go with the second or third stage cooling, or we go with the ONAF or OFAF type cooling. So for the higher rating transformers, we select two-stage cooling, ONAN and ONAF, or we can select as the OFAF as well. This we can three-stage OFAF as well. ONA is my natural, ONAF first stage, and ONAF is my second stage. So if we move from ONA and cooling to ONAF, we get an additional 25% higher rating from the same transformer. At the same time, there will be additional auxiliary losses due to the fan and motor, but that could be managed because I'm getting higher 25% as higher output. So for a small distribution transformer, the ONAF cooling is not advisable as the auxiliary losses are also added. Whereas for the higher power rating, adding the second stage coolings is recommended as the output power increased. Am I clear with the cooling? Where we take what kind of the coolings, and when I'm taking the cooling, so how this like power is increasing. If you see this transformer, if you see this, let us see this SLD snapshot. So what they are telling means they have not written here, but they have written 200 MB, but we write here three ratings: that rating on the ONA, the rating on the ONF, and the rating on the OFF as well. Here we can see in this particular diagram. ONN, ONAF, and OFAF. Here ONN 60% of the power ratings. ONF conditions should be 80% of the power rating, and OFAF is 100% of the power ratings. Just give me 1 minute. Yeah. We can
Dago
see.
sir,
Yeah.
at what MVA level above we are using OFIF?
Generally more than 10 MBA.
Okay.
Yeah. Like 50, 60 MBA. Some company take more than 50 MBA. For 100 MBA they take. I mean, generally 10 MBA you can, it could be used. Okay, I hope I'm clear with the three topic we discussed, three concept we discussed here. Let us summarize those. What we discussed about the losses. I hope I'm clear on that. Then we discussed about the rating, and then loading, deratings, WTI, OTI, and then we discussed about the cooling. Now, coming to the next transformer selections parameters, which is the percentage impedance of the transformer selections. What we do, or how we do of the impedance selections. This impedance is play a direct role in the short circuit current. And if I tell one example, okay, I will come on this example later on. Let us start with the basic. What mean by the percentage impedance? The percentage impedance of the transformer is nothing but a measure of the volt drop when the transformer is on full load due to the winding resistance and leakage reactance and expressed as a percentage of the rated voltage. In other words, it is percentage of the ratio between the full load short circuit terminal voltage to the nominal voltage of the transformer and denoted by the percentage Z, where Z is called as the impedance. This is some basic definition of the transformer. And now from where the impedance we select. So in order to select the impedance of the transformer, we follow the IEC 60076 part number 5, page number 13, table number 1. This is the reference for the impedance selection of the transformer. Is the international IEC standard guidance for the impedance selections. Few company like that manufacturing the transformer in India, they sometimes follow the local standard as well. Few company local country specific manual, like in India the CPIP manual is sometimes they also follow that manual for the selection of the percentage impedance. So let us see that. I have taken both percentage impedance value. Let us see. Up to 630 kVA, 4%. Up to 630 kVA, it is 4%. So both internationals and local country specific matching. 631 to 12505% is 5%. 6.25 here it is 6%. Right? And then 7%, 7.15%, 8, 8.35, 11, 12.5, 12.5. So if you see any transformer rating which is more than 100 MVA, all those transformer rating percentage impedance generally we take 12.5. Are not 100 MVA, 63 MVA also. Any transformer which rating is more than 63 MVA, their percentage impedance generally we are most of the time we take 12.5%. This is standard as per the IEC. For the smaller transformer, this percentage impedance is changed. Let us see the impact of the impedance on the system and why the correct impedance selection is important, and what we can and where we have to change the impedance, where we have to go non-standard impedance for the electrical system. So this is the impedance that we follow. The impact of the impedance is the effect of transfer impedance, percentage impedance in the overall electrical system. If the percentage impedance is low, the short circuit current at the transformer LV side electrical system will be high. On the other hand, it will reduce the voltage drop in the transformer winding, and which will enable better voltage regulations if we have the lower percentage impedance. Short circuit current lower, and it will reduce the voltage drop in the transformer winding, and which will enable better voltage regulations. If in case we have higher percentage impedance, in that case, then the short circuit current at the LV side of the transformer will be less. Just give me 1 minute. Yeah. So if the percentage impedance is high, then the short circuit current at the LV side of the transformer will be less due to higher impedance by trafo, but it will increase the voltage drop in the transformer winding. So means like carefully we have to select the transformer impedance, because if it has some advantage, at the same time it has some disadvantage as well. Therefore, the percentage impedance of the transformer must be precisely selected to maintain a proper balance between the short circuit current level and the voltage regulations or voltage at the LV side of the transformer. And selection usually done by IEC 600 part number 5 is standard. But if my short circuit current getting too much high, in that case we have to modify the percentage impedance. In few cases, the generating power plant, particularly in the generating power plant where the LV side short circuit current comes higher, in order to minimize the short circuit current under a specific level, it needs to increase the impedance from the standard value. Like here we can see, I have taken a CBIP manual, which is a local Indian country designing manual. So I have taken the CBIP manual for the 6.6 kV by 433 voltage auxiliary supply distribution transformer, and for the LV system basically. So they are telling, this is manual is telling, at the LV side, the impedance value of the transformer shall be so chosen as selected as to limit the fault current level of the 415 voltage system, preferably to 36 kiloampere. But this requirement is not possible if fault current level up to 45 kiloampere shall be adopted. Means they are telling that fault level at 400 voltage side, which is generated by the transformer, that should be less than 45 kiloampere. So in that case, here I have example, like this is 11 kV by 433 system we have, and we have 3150 kVA, and in that case, the percentage impedance that we have taken is 10 percentage. We can simulate this as well. Like here, if we go and if we simulate the fault current, let us simulate the fault current. U23 out, U24 out, and again if we simulate U25, let us provide some short circuit rating. This 11 kV, so I'm providing here some 25, 35 or 25 kiloampere. X value is suppose putting 10. And click on the OK. And then if we run the short circuit current, and then if we see the fault on this bus, it is how much coming? 105, right? 105 out of 105, 40 kiloampere.
89.
40 kiloampere is injected by this lump load, but 66 kiloampere is injected by this transformer on this system. So 66 kiloampere fault current is very much high, which is injected by the transformer. On this bus bar, the fault current coming 105 kiloampere. It is high. In that case, let us see the impedance. We have taken impedance 7.15. This ETAP also take the IEC only. So this is 4 MVA. So as for the 4 MVA, what should be the rating? 7 ampere, right? No, 7 percentage for the 4 MVA. For the
Yes,
4 MVA,
7%.
7 percentage.
Yes.
So here they are taking 7 percentage, 7.15 percentage that they are taking, right?
Yes.
So
Yes, sir.
now what I can do, now we have to change the impedance to a non-standard impedance. Now let us suppose I am taking a 10 percentage here, 10 percentage. Now no need to go typical, no need to select this. I'm taking 10 percentage impedance here. And then if we run the load flow, then could we see the fault current, it is reduced to 50 kiloampere now. isn't it?
Yes, sir. Right, right.
So that was earlier 66 kilometer, now it is reduced to 50 kilometer. So in that case means when the fault or short circuit current coming very much high, we can alter the impedance, we can change the impedance. Okay, and in this particular case, I have taken the extract of the project in which the percentage impedance in this particular project it is written as 10%. The reason, it is 3150 kVA transformer. It is so for 3150 kVA transformer, ideally for 3150 kVA transformer, the percentage impedance should be 6.25%, right? It should be 6% or 7% in this range. It should be. But I have taken 10% here. So why I'm taking 10%? Because of I wanted to reduce the fault current due to this reason. So now moving to the next parameter in the transformer, which is the tap changers, their selections. So I hope I'm clear with the percentage impedance, what we follow, and sometimes we like alter that percentage impedance as well. So coming to the next parameter selections, which is the tap changer selections. So selections, why I'm putting it, because we have two type of the tap changers. So tap changers are, let us see first of all why the tap changers are required. So the and where it is located. So tap changer are required to regulate or keep constant the secondary or LV side voltage of the transformer. Suppose I'm taking the percentage impedance and my LV voltage is decreasing on the bus bar, the voltage is decreasing. So in that case, I can change my tap, and through that we can regulate the LV side voltage. So the tap changes are required to regulate or keep constant the secondary LV side voltage of the transformer. So this tap changer regulating or controlling the LV voltage of the transformer. First of all, there are two type of the tap changers used in transformer, and based on importance and voltage level it is selected. That could be OCTC. This stand for the off circuit tap changer, used in small distribution transformer due to limitations in transformer size. This OCTC use. And when we go with the higher rating of the transformer, in that case we use the OLTC. So when we have the OCTC, this is off circuit tap changer, means we have to de-energize the transformer. I'll show you one transformer nameplate. I'll show you if you see, this is a transformer nameplate, which is a 200 kV transformer, and on this nameplate it is written here, disconnect supply before operating off circuit tap switch. So this, since we are disconnecting supply due to this reason, this tap changes we are telling as off circuit or OCTC tap changer. Only tap changes means no need to disconnect the supply, no need to disconnect the load. In the supply, in the operations, this tap could be selected or adjusted. So it is used in large power transformers. It is used in large power transformer size, maybe more than 5 MVA. OLTC is not recommended for 11 kV and below 5 MVA. Location of tap changer in transformer, it should be located on the primary side, or more accurately, if we say, it should be located on the high voltage side. And purpose is to regulate the low voltage. So why we take the tap changer on the HV side? What is the reason on that? As the primary or HV side voltage is higher, power is same, then current will be lower. So we are changing the tap, through that there might be, or means we are in the tap changer, what we have the windings. We have the windings. Now we are changing the winding positions, that where this winding now will connect. Right. This is what we are doing with the tap changer. Tap changer. So if I place this tap changer on the HV side, when the voltage is higher, then current will be lower. And then during this changing of the tap of the winding, the current would be lower. And when the current is lower, then arc which is generated by the current, this arc also would be lower. So due to this advantage, the tap should be located on the high voltage side. So HV current is low, so making and breaking of current is easy compared to the secondary side. And on the HV side, the number of winding turns is higher, then more accurate in tap changing and accurate voltage regulations possible and smooth variable variations possible. Third reason is that HV windings are mostly placed on the outer side of the core coil assembly, and it is always easier to bring out taps from the outer winding as compared to inner windings. So this is also one reason that we place tap changer on the HV side. So since OLTC is a mechanical device, tap changing, it is a mechanical device. So to operate the OLTC, we will need the automatic voltage regulator panel, AVR panel for the transformer. The AVR constantly monitors the voltage and provide tap changing command to the motor of the OLTC whenever required to regulate the secondaries or LV side voltage. So if I show you any transformer internal winding, if I have, it is not located here, it is not here. Otherwise, we take a separate mechanism for the OLTC.
Okay, sir.
And about the OLTC, how we select the tap or how many tappings required, this point we will discuss in the ETAP module when we will discuss about the load flow analysis, and then at that time we will discuss about the OLTC selection, OLTC, how we decide the OLTC in the transformer. So this OLTC I'm putting on hold and we will cover in the ETAP module.
Okay, sir.
So tap changer range we will discuss in the ETAP module along with the simulations by ETAP. Okay, so should we discuss further? Like we have some concept about the installations, transportations. Should we? I think I have installations, transportations. Then it will take another 1 hour. Thing if you all allow 30 minutes. I think 30-40 minutes. Is that fine for all of you? Should I continue? Okay. So let us discuss.
Yes, sir.
Let us discuss about the some transportations, installations, concept about the transformer, and mainly I will discuss. This point is very much important in case of the solar power plant about the installations location of the transformer. So about that, I will also cover that point. So let us start first with the transportations. Now, like all the parameters you have selected and then sent order to the manufacturer, they are manufacture that transformer. You have done the fat transformer is ready to dispatch. So during the transportations from the factory to the site locations, the transportation of the transformer is very critical. So extra care needs to be taken to avoid shocks, impact, and damage during the transformer. The shock detectors will be installed on the tank of the transformer to monitor the shock during transportation of the transformer, and a proper route service to be done before the transportation of the transformer. Each power transformer is to be fitted with the removable wheels to enable a smooth bidirectional movement during the installation at the substations, and fitted with a device for blocking and wheels after installment. Blocking of the wheels, we do the wheel blocking after the installment as well of the transformer. So during the transportations, due to the transformer's heavy weight, most power transformers are transported without oil and without bushings as well, and as without other accessories also. Without any accessories, it is transported. Like all bushing, each and everything we have removed from the transformer during the transportations. And instead of the oil, the transformer tank could be filled with nitrogen gas or dry air gas. The purpose of the dry air or nitrogen supplies system is to maintain a dry atmosphere at a positive pressure within the transformer tank to avoid taking atmospheric air and the moisture into the tank. And this helps to preserve the dry state of the insulation until the transformer is refilled with the insulating liquid at the site. The internal gas pressure should be high enough to assure that it will remain positive during any expected low temperature during transit, especially during the mountain crossings, long distance or long duration shipment of the equipment may require external gas bottles, and regulator control the ensure positive pressure is maintained throughout the shipment of the transformer. The reference standard is IEEE standard C57 150 2012 is the year. IEEE guide for the transportation of transformer and reactors rate for the 10 MVA or higher rating. So if required any further informations, you may please look for this IEEE standard as well, which is guide for the transportation of the transformer. So when the transformer is like when you are making the electrical installations layout drawing, in that electrical installation layout drawing, we need to make sure, or we need to provide the arrangement for the transformer transportations as well. So near to each transformer, we should provide the approach road as well, so that the vehicle which is carrying the transformer, they can reach to that point and they can like install the transformer at that position. So in the layout drawing, make sure to have the road near to the place which is decided for the transformer. So during the substations electrical installations layout drawing preparations, we need to ensure the road up to the transformer installations positions, and road width would be suitable for trailer and crane for easy movement in the subsistence compound. Generally, the road which we take, the main road and road that we take near to the transformer, that road width we take around 5.25 meter. Around 5 meter road we take, right, near to the transformer, and other internal road in the substance we take as 3 meter road or 3.75 meter road. And when we are doing review the transformer general arrangement drawing, we need to comment, or we need to ask the transformer vendor to indicate the transformer direction of withdrawal, that in which directions the transformers need to be withdrawn. So the transformer direction of withdrawal shall match the substation's layout plan. So like here, we have a direction of withdrawal here, and here we have the road. So here we can withdraw and road coming here. So directly, and here we need to put the rail come route. For the rail come route, we take the transformer to their desired foundation, right? The power transformer are normally filled with the insulating mineral oil. However, transformer using a sub-6 gas are environmental friendly, biodegradable K-class oil are ester oil or synthetic natural ester oil having higher fire point. Those oil is having higher fire point compared to the mineral oil are also being considered for transformer by a few companies, and these are the nature friendly oil, this ester and oil compared to the mineral oils. So few companies also consider those kind of the oil as well. And when we are installing the transformer in the foundations, we need to provide the oil soak pit and oil collecting pit as well, because as we have discussed that a transformer have the tank radiators, and those are externally attached at the side. Those are not a common enclosure, they are attached with help of the nut bolt washer, so there is a possibility to leakage of the oil. So this oil we collect into the soak pit, and then it is further connected with a common oil collecting pit, and those oil further we can uh, like uh, uh, can filter, and then again we can use also to top up the transformer oil. So oil filtration unit required generally, as per the general concept. An oil soak pit of adequate capacity should be provided below each oil-filled transformer or reactors to accommodate at least 150% of the full quantity of the oil contained in the transformer tank. Alternatively, a soak pit of adequate, this is one option. Second, alternatively, a soak pit of adequate capacity to accommodate 1/3 of the total quantity of oil contained in the transformer or reactor tank, and a common remote burn oil collecting pit have capacity at least equal to 150% of oil quantity in the largest size transformer. If in case we have 2 or 3 transformers, then we have to see what is my largest size of the transformer out of that is provided for a group of transformers or reactors. The bottom of soak pit below the transformer should be connected to common burn oil pit with a drain pipe, or we can use the hewn pipe or concrete pipe of minimum 150 diameter, or sometimes PVC pipe. Few company also use 100 or 150 diameter for fast draining of oil and water through gravity from the soak pit to burn oil collecting pit, which is generally located away from the transformers or reactors. Let us see the some same concept which we follow in the when we prepare the transformer uh, foundations in the layout drawing. So if you see here, we have 3 transformers, and then here we have the foundations of the transformer. In the foundations, this small portion is indicating the soak pit. Now here we have a common oil front collecting pit, oil soak pit that we are telling, and all the this oil collection pit which is uh, connected with each foundations. We are taking the pipe that could be a 150 pipe for drop of oil collecting, and all the pipe then collect going with to the oil soak pit or burn oil pit, and further this oil we can take and we can filter and we can again reuse as well, right? So this during the layout drawing preparations we have to ensure this arrangement as well. Now about the transformer noise level, acceptable noise level, and this parameters is important when transformer is located or installed in a residential area or near to residential area. So whenever a transformer or switchyard is located near residential area or any residential building, a special attention is required to the noise level value of the transformer. The transformer noise level measurement will be in accordance with IEC 60076 part number 10. As per UK engineering practice, the noise level should be less than, should not exceed 73 dB decibel, 73 dB at 1 meter away from the radiator surface, whereas in India, the limit is 75 dB. So at 1 meter away. So the noise level should not more than 75 dB. This is what generally acceptable. Now, as we discussed that transformer, tank, radiators, all radiators and connecting with that tank with the external nut bolt washer, they are not integral with the main tank enclosure, and there is a possibility of the oil leakage. So due to that oil leakage, there is a, if any arc current is flowing and any arc happened, there is a possibility of the fire in that near to the transformer. So in order to protect the other transformer from the fire, we need to provide a fire barrier wall near to each transformer. And sometimes when we have transformer and the control building, in that case, either we take the enough distance between the control building and the transformer, or the transformer wall we have to design, or the control building wall we have to design based on the fire rating requirement. So fire rated wall we have to design. So either take the proper gap between the building and the transformer, or design wall with the fire rating. In case of the transform control building and the transformer, and suppose we have more than one transformer, in that case between two transformer we need to provide the fire barrier wall, and the dimension of this wall we take as per the transformer GA, and the wall dimensions should be more than, generally we take 500 MVA to 600 MVA. So take the full GA and then extend 600 mm above the transformer, considering that if any fire happening, so it can go to 200, 300, 400 above the transformer. So we take the margin higher, 600 mm higher we take of this wall. So in addition to the
Sir,
socket,
is it with respect to conservator tank?
yes, the oil,
Okay.
where you are putting the oil.
Okay.
So
Okay.
your main tank, and in the conservator tank also you have the oil, right now. So 600 mm or 500 mm above that. In addition to the socket provision, if the oil capacity of the transformer is larger than 5000 liter, the suppression valves or fire barrier valve must be provided at the site between the transformer and between the transformer and nearby control room building. In case required killers are not available as per the NFPA or as per the S1646 or any country specific standard, if they are telling, or any national regulations. Generally, we follow the NFPA. The suppression walls or fire barrier walls should be minimum 4R fire resistance rating. Means they are taking that if any fire happened, you are calling the fire uh, brigade. They are coming. So from their movement to the fire station, road traffic to the substations, it will take around 3 to 4 hours. So generally we take enough 4R rating of this wall. So 4R fire resistance rating, and thickness of wall we take around 230 millimeter, and it is made with the RCC materials. So this is for the like for the firewall, and when between transformer the separating wall are only provided when the oil capacity of the transformer is larger than 5,000 liter. In that case only, if less oil, then separating wall is not required. Between transformer and control room building, the suppression wall must be provided in case control room building is located at a clear distance or direct distance of not less than the value mentioned in below table. Means, let us take the below table. Let us take the table. So what we do, in case we have transformer in that, first of all, below 5,000 liter, no need to consider anything. But in case in your transformer the oil capacity greater than 5,000 liter and up to 10,000 liter oil in your tank you have filled for the cooling of the transformer, then from the nearby control building we need to provide a clear distance of 8 meter. Where it is important, I'll here we have, suppose here we have a solar power plant. This parameters is very much critical. Let me check if I have any solar power plant. So here we have control building and here we have the power transformer. So from here to here, this distance is important. Sometimes what we do, let me take the snapshot. In this particular case, my 33 kV is outdoor. Sometimes what we do, 33 kV panel we place inside the control building, and we take the 33 kV cable out from the HT panel connecting to the transformer, right? 33 kV side that step up into 220 kV or 132 kV and then feed to the grid. Since here we are using 33 kV cable, this cable is costly. We wanted to optimize the spacing between the room and the transformer. In that case, we have to check what is the transformer oil capacity we have, and then refer to this table. If in this range, minimum 8 meter clear is separating distance required. To avoid the firewall wall below or the minimum distance, or we can say a separation wall must be provided if clear distance is less than below distance as stated in the table, 5,000 to 10,000. If my oil capacity up to 20,000 liter, then 10 meter, 30,000 liter, then 12.5 meter, above 30,000, then 15 meter spacing we have to provide minimum. Am I clear? How to get this oil capacity?
Yes, sir.
So you will get this oil capacity from the transformer nameplate or transformer GTP. I have taken a transformer GTP. For the oil capacity of individual transformer, the transformer oil capacity is indicated by the transformer manufacturer in the technical datasheet or in GTP or on the nameplate. Below is extract from a 50 megawatt transformer dataset. In 50 megawatt transformer dataset, the oil weight is 18,200 kg. Now you can convert this kg into liter, right? Correct? Huh? And then take this oil liter and then go with the, here I have the this is my 50 megawatt solar power plant, right? Here I have the control building. In that we have placed the HT panel here. So all the 33 kV cable coming from the ICR, that we have here, and those 33 kV cable feeding to a common bus bar, which is here, and then we have one single output which is connecting to the power transformer, which is step of 33 kV, into 132 kV or 220 kV. Here if you see, I have indicated the cable and the cable trench. So when you prepare the layout drawing for solar power plant, you must have to mark the distance between the transformer foundations. Do not take the GNO, you take the transformer foundation as a reference to the control room building, this distance. Could you see here in this particular layout drawing, 10,320 millimeter mark, right? Could I reduce below 10,320 millimeter? Because I'm using the cable, so I want to keep as close as possible so that I can minimize the cable length, and then I can minimize the cable cost as well. Could I minimize this?
No, we need to maintain minimum 10 meter.
Because go to this table now, and up to 20,000 liter. Here I have 20,000 liter. Suppose for 20,000 liter, my requirement is how much? 10 meter. I cannot take less than 10 meter. So due to that reason, I have taken here 10 meter, 320 mm, or you can go 10.3 as well. Means you need to ensure it should be more than 10 meter. Am I clear? Am I clear?
Yes, sir.
This is very much important for solar power plant engineers, because they have to prepare this kind of the drawing for the power plant installations. Now,
One thing regarding fire damage zone across the transformer, how that is established?
damage zone is the, here we take, now as per the rating we take what is my oil capacity, and then accordingly as per the NFPA we take the value, and we make one circle indicating what is the that transformer damage zone, and any other oil containing equipment should be out of that transformer damage zone, which could have any oil.
Okay.
So now coming to the transformer purchase order specifications preparations. So when we prepare any, when we have to procure the transformer, we have to prepare some technical specifications. So let us see what is the minimum informations, what are minimum uh, uh, technical uh, input we have to provide to the manufacturer to get the quote of the transformer cost or price. So I'm taking three different level of the transformer: 400 to 220 kV substations, 220 by 132 kV, and then 130 by 33 kV substations. So let us start with, so 400 to 20 by 33 kV substations. My power rating generally that we take 500 MV, so I'm putting the power rating, and we have to write tertiary is my 167 MV tertiary rating, three phase or three into single phase, whatever as per my site where it is located. Auto transformer, then we have to write the vector group, which is YN0T11. Then we have to write what is the cooling type. Then we have to write what is the percentage impedance. Above 63 MVA, we take 12.5 percentage. I'm putting 12.5 percentage. And we are allow some tolerance, which is as per IEC. So we can write here this percentage impedance with IEC tolerance. OLTC, about tap changes we have to write here, and about the OLTC range also we have to write here, the plus minus 10 percentage for HV variations in the steps of 1.25 percentage, and then we have to write how many steps required and 220 kV side of series winding, because this is auto transformer, maximum flux density in any part of the core and yoke operated MVA, voltage and frequency should not be more than 1.9 Tesla. If we require the dissolved gas analysis, online is nowadays most of the company taking DGA, so we have to write here that we require the online DGA. Whether the bushing is oil filled bushing or RIP bushing, what kind of the bushing? So we have to write here oil filled condenser bushing with testing tap and overload capacity of the transformer as per the IEC 60076 part number 7. This is auto transformer, same here it is coming. Just the voltage rating is changing. Here it is now 2 winding transformer, 100 by 33 kV substation, so 3-phase 2 winding. So far it is single winding auto transformer, 2 winding power transformer with Y1 vector configuration, cooling impedance at the principal tab with the IC tolerance, OLTC range and OLTC steps, flux density, and then type of the bushings, oil filled condenser bushings with test up and overload capacity as per the 60076 part number 6. So minimum this information we should provide to any vendor to quote the transformer price. Let us see a transformer nameplate. So this is a distribution transformer nameplate. So I think the first one is clear what is meaning of this: disconnect supply before operating the obsolete tap changer. Station transformer. This is the Indian standard IS 20226 they follow locally here. Rated kVA, HV side voltage, LV side voltage, and here need to make sure that this LV side voltage should be no load voltage. This is important here, not the full load voltage. The full load voltage would be 400 voltage or 415 voltage, and full load voltage, and no load voltage is 433 voltage. Rated current HV and LV side, phase, frequency, connection symbols, year of manufacturing, type of cooling, oil temperature rise, winding temperature rise. Winding is the main source of the temperature rise. So here we take 5 degree more margin. Guaranteed impedance 4% because it's 200 kV is 4%, and then volume of the oil 420 liters only. They need to put in the nameplate as well. Mass of the oil and tanking mass, total mass, maker serial numbers, tap changes, MCTC. I hope this all parameters we have discussed, we have covered, right? So now we have the transformer modeling in the ETAP. I think we will discuss this topic when I will come on the ETAP topic, and then I will tell how to
Sir?
do.
So one question, sir.
Hold on. How to do the modeling of the transformer. So when I will come on the ETAP model, I will take the transformer modeling as per the ETAP. Okay, so this is that's all from my side for the transformer topic. Yeah.
Sir, for OLTC, we have seen somewhere we have written there that the OLTC range minus 10% plus 5%, and somewhere we have written that 16 step, 10 step. So is there any standard for that? Which type of capacity?
We will discuss about when I will come on the ETAP. I will discuss about the OLTC.
Okay.
Yeah, you don't worry. I have already written this topic. When I will reach on the ETAP, I will discuss this. The taps in the range we will discuss in the ETAP model along with the simulations by ETAP.
Okay, sir. Thank you.
Raghav sir, one doubt.
Yeah, Raman.
Regarding the transformer installation, you have said that the direction of withdrawal need to mention by the vendor.
Yes.
How that will normally we will decide which direction we need to withdraw the transformer. No? That may be in towards the HV side or LV side. How they will decide?
Means you can ask him to mark because there is a wheel attached
Yes.
on bottom of the transformer, right? So you have the vendor will see that what is the direction of the wheel movement.
But when we are designing that thing,
So
that is our option to withdraw.
So in that case, you can ask to him, and if their option is not matching with your layout, then you can propose another, and you can discuss with the vendor to adjust the withdrawn direction as per your comment or as per your desire at the site.
Okay, sir.
Yes. So
Or
Sir?
one doubt in slide number 96.
Yeah, let me go there. Yeah, 1 second. Yeah,
Sir, in this one, the transformer bushing CTs we are selected at 1000 ampere, but in the case of core 2 for WTI, we have selected 600 ampere only.
correct. Yes,
But the actual current rating is nearly 524 amps.
but
But
524 is not the standard rating for the CT. Due to that reason, 600 we have taken.
that I understand. But why we are going for HV bushing CTs 1000 ampere?
Actually, using CT, we have taken means again you have the options. You can reduce this 1000. You can go 600 as well. That one. Here we have
Okay.
taken
Uh,
more also. That you have since actually what happens. This is a grid substation project, so we have follow the grid technical requirement for the CT rating.
okay.
So due to that reason, this CT ratings coming 1000 here.
Okay, sir.
If I check that tender, I think I can show you in that RFP. So I have like here we have follow the technical specifications for the CT. Anyway, CT sizing we have discussed, so you can go as per that rating.
Yes, sir. Yes. Because normally bushing CT is included with the transformer scope. That may be
Yeah,
a reason.
yeah.
And also one doubt in slide number 87.
Okay. 1 second. Power transformer. This is a technical specifications and then breaker of the project, isolator, and then CT, current transformer. So if you see here, what they have written 220 by 1600 to 132 kV 16800. So as per the like technical specifications, now I have to check what is the technical specification of that project. So as per that we have selected.
Okay, sir.
Okay, but here this manufacturer will select this, and we have to see that when we are making the SLD and we are indicating that CT, so that should be near to the transformer full load rating.
Okay, sir.
Yeah.
Sir, in this one, you have shown that for 51 NS, you have provided a PS class CT. Is it necessary to provide the PS class for 51 NS? Because REF, we are normally using PS class, but 51 NS,
No, no,
that
no,
is
not necessary. Not necessary.
not necessary. Okay.
Yes.
Sir, one more doubt in slide number 87. Sir, in this one, the vector group you have mentioned for HV and for intermediate winding, but in the case of LV, that is not mentioned in vector group. Uh, is there any particular reason?
LV is 33 kV, na here,
Yes, yes. LV is 33 kV,
which is delta. Na?
but in vector group that was not mentioned. Na?
Delta is mentioned in the vector group. This is the vector group. Na? See, this is auto transformer. Okay. So 400
Okay,
and 400 and 220 kV, we have single winding, which is star connected, right?
okay,
Then neutral we are taking.
okay,
This
okay,
is
sir. Okay.
this is auto
Yes.
transformer. So A coming
Okay, okay, sir.
between 400 and 220 kV, the phase displacement is 0 degrees, so 0 coming here.
Yes, sir.
33 kV is delta winding,
Delta, okay.
and between 33 kV and HV there is 11 degree. 11 is the phase displacement.
That's clear. But in the case of IDT transformer, inverter duty transformer, when we are representing the percentage impedance, then normally I have seen HV to LV that was mentioned. Sometimes LV to LV1 to LV2 is also sometimes they have represented. Is there
Yes.
any reason for that? Because
Yes,
where we
we indicate between each winding what is the percentage impedance that will indicate. I'll come back on the IDT snapshot.
yes sir, slide number 60.
Yeah, so here if you see 11 by 800, 800. So this is 800 by 11, 800 by 11, right?
Yes. That's
Then here we have the vector group. So HV is my star and HV come first in capital. So star here and here, but neutral not neutral but not grounded here. Grounding not done here. Y and D11, D11, DD here, right?
okay.
Percentage impedance without negative tolerance. Here they are not indicated the percentage impedance. Generally, we should indicate between this to this, between this to this, between this to this, what is the percentage impedance that should be indicated.
But what is there any particular matlab, that means when we are is there any area we are using that impedance for calculation in between LV1 to LV2?
No, Kyle. As per the standards we follow, no? This is C5 MVA transformer, right? So for the
Yes,
5 MVA, what is the standard we follow? What is the value we follow?
6.25.
6.25, no? As per the standard
IEC table.
IC cable, no? 6, where is the rating? How much the
6.
rating?
5.5. 5.5 in it is 7.15 in this table, and this is 7%.
5.5, no? Yeah, it is 7% here, and here 7.15%.
Here it is 7.15.
Yeah. So I think now you can check the IS as well, what they have taken. 6.5 is the 4350. Generally, we follow this IC, and based on that, we indicate the percentage impedance.
Okay, but in between LV1 and LV2, the same value will come because
Not. A different value will come. You can check this specifications here. Like there is a transformer specifications. In that, if you check the impedance, both this impedance is altogether different. Let us see any three winding transformer, or let us see this auto transformer. So if you see, you come on the impedance value, losses, no load, full load auxiliary losses, and come to the impedance.
yes, sir, this one 7.8.
Yeah, could you see here now? HV to
Yes.
I, right? HV to IV, then HV to LV, then IV to LV, right?
Yes, sir.
The impedance. And now the value you can see here 10.3, 12.5, 15.4 at maximum principal and minimum tap. 3 tap we have, right? So the tap,
Okay.
the impedance that we take, that impedance we take on the principal tap. So principal tap 12.5. At maximum tap and minimum tap, this impedance is changing, right? Now, if you see between HV and to LV, which is 33 kV, right?
Yes, sir.
The percentage, the impedance is 60.
Okay.
And between IV, which is 220 kV, so between 220 kV and 33 kV, this impedance is 45.
Okay, sir.
So generally, we need to indicate impedance like that: HV to LV1, HV to LV2, and LV1 to LV2.
Okay, sir. I think this impedance calc means how we are using this impedance. We will discuss in calculation part.
Generally, we follow as per the standard round. If otherwise, if any time permit, I will try to discuss that.
Okay, sir. Okay, okay. Thank you, sir.
Yeah.
Sir, I have one doubt actually.
Sir,
Yes, yes.
sir,
Uh,
we have what we have seen that the distance between the building and transformer generally we have seen. But what is the minimum distance between transformer to transformer to be maintained for the avoiding fire incident? Is any IS or for that
Same Avinash.
same, sir?
As we discussed for the transformer and the control building, if your transformer oil in the transformer is more than 5,000 liter, so same concept apply there as well.
Okay. And if the distance is not available, then we have to put the firewall.
Yes,
Okay. Thank you, sir.
yes. And between the firewall and the transformer, generally we take approximately 1 meter. The clear passes we required. Okay.
Okay, sir. Thank you.
Hello.
Yeah, Rajkumar.
As I mentioned that WTCT secondary is not normally 1 amp, it's something 1.3, 1.5, 2 ampere and all this. Different manufacturer it is saying actually.
Yes.
Is it anything beyond that?
So that generally manufacturer decide, Rajkumar.
Ah, that I also found some different values are there. There is no standard actually. That is the reason I
Yeah,
also.
no standard. Generally, the manufacturer decide based on their like what sensors they are using, the resistance.
Uh-huh.
So generally, we keep this in the manufacturer's scope.
Okay.
Yeah.
And one more thing, you told that in UK they are using YD1 and that zigzag earthing transformer they use for earthing and all. What is the advantage in that actually, sir? Instead of the similar arrangement we also used in Qatar actually. They used YD transformer and there is 32 or 40 MA transformer. After that they put the earthing transformer and everything. Nowadays they are not using. So what is advantage in that actually for YD1 actually? Why they are selecting YD1?
Advantage, like what you have the delta winding.
Mm.
So in delta winding, we have discussed what are the advantage of
Zero.
delta connections.
Yeah, that is okay. Yeah,
So same advantage you apply
that is
here.
the only one thing.
Yes.
Okay, sir. Okay, okay.
Yeah.
Sir, I have some doubts.
Yeah, Krishna.
Sir, usually I was noticed that the WTA CT is placed in center phase, Y phase. But some manufacturer they're providing in any phases or first phase, R phases or B phases. Is there any standard to recommend a manufacturer to place the WTA in Y phase?
I'm not aware on that. I don't think there is any standard exist. If I came, I'll discuss with any manufacturer. If I like came to know anything, I will definitely let you know, Krishna.
Normally, Wi-Fi
Yes,
is the
sir.
balanced load. Wi-Fi current is the common for other two phases also. It became like that only. No, sir. Some from ACDB and distribution board we put that ammeter and CT are the Wi-Fi only. R and B we are not providing.
This
Is
is
it
So which
like
one will
that?
be the
yeah,
which one will be the suggestible, sir?
yeah, this is like a conventional standard practice that we follow, but I'm not sure about any standard where it is mentioned. If I came to know, I will let you know.
Most of the trends are 100% that some they are providing in the Wi-Fi only.
Yes, yes.
Whatever he is saying that is a different issue. So I was also
Generally it go to the center phase. Generally it
yeah.
goes to the center phase, but uh, for R phase, B phase, uh, I have not seen.
I
And
have
if
also not seen. That's the reason, sir.
and if any standard,
Yeah, sir.
I'll
Some distribution manufacturers they are providing in R phase, sir.
in distributions it may not be so much critical because the transfer rating is small. Okay, Krishna.
Yes, sir.
The 200 kV, 400 kV, like the kVA rating in the kVA, right?
Okay. So if the kVA ratings increase, so
then
shall
it
we
is,
monitor all the three phases and secondary also, sir?
yeah, yes.
Okay. So my second question is also clear now. So, sir, I have this flux density selections.
Yes, yes.
From where I can pick these values of 1.9 Tesla
1.9
something.
Tesla, 1.9 Tesla, I think as per the IEC standard, Krishna. This is recommended in the IEC.
Oh, for all the voltage
Yes,
levels, sir?
yes, yes.
Okay, sir. This
Rating
is
voltage.
okay.
Yeah.
In my project, I practically noticed that in solar project, I was installing 1.5 MA solar into the transformer. While the solar generations, the active power is reducing, but the reactive power system remains same. In this case, is there any standard that how much capacitor I can load it in this single transformer?
I'll come on this. When I will come on the capacitor bank sizing, I'll come on that, Krishna.
Is it related with the capacitor bank calculations or
Yeah,
transformation?
we have in the ETAP the capacitor bank sizing, then I will take up this point. Basically, capacitor bank is injecting or providing the required reactive power. I'll take up this point when I will reach on the capacitor bank sizing.
Okay, sir. Okay, thank you. Miss.
Thank you, Krishna. Okay, so from next week, we'll start the module number 4, which is the single line diagram SLD module. So now we will coming on the drawing preparations. Okay.
Okay, sir. Thank you, sir.
Yeah. Thank you so much. Thank you.
Sir, hello, sir. One more question is that, sir. This DY11, if the vector group is changed, the DY1 transformer acting as a load. Can you please explain how it is acting as a load, sir? In this heat, have you shown some?
Because of the voltage angle changing. So due to that reason, it is acting as a load. And there is one general concept that the power flow, active power flow from higher voltage angle to the lower voltage angle. So due to the
Yes,
voltage angle changing, it is acting as a load.
Yes, this explanations I'm not getting clearly, sir. So I just confused.
No problem. When I will come on the ETAP topic, I will again take up this. You don't worry about that. Okay, you
Okay, sir.
have a double think on that. I have given you the hint that is the voltage angle. Okay.
Okay, sir.
And,
okay.
Take that point as a reference, and then you think it will be clear. Otherwise, you don't worry.
Okay.
I will take in class. Okay.
Okay, sir. Okay. Thank you, sir. Thank you very much.
What is the voltage system for the your transformer? And we do have SVC better than capacitive SVC, SVG. Nadim, your query is not clear to me. What is the voltage system of your transformer? We do have.
Oh yes, sorry. I was just sending the message for this other participant who was asking you about reactive power, as we have a static. It is static VAR generator, a kind of reactive power generator to compensate. Reactive power and harmonic.
Same we can take from the transformer. We take. Let us take the example of 100 MVA. So we can take 100 MVA active power, or we can take 100 MVA reactive power. The capacity curve of a transformer is nearly circle. So we can take 100 MVA or 100 MVA. No matters. Okay.
Okay.
Yeah.
Sir, if I loaded 100 MVA reactive power, it will be a double loaded or not? So
No,
it will be overloaded also.
Either you can load with 100 MVA active, or you can load 100 MVA or reactive as well.
So in this case, should I install another transformer to compensate the reactive power for the solar project?
No need to install. They have the SVG, and for that purpose they are requiring one transformer. So they are asking what should be that, and their SVG is rating is the MVR rating. So for that MVR rating, what should be the MVR capacity of the transformer?
So if if 5 MVA transformer is there,
So
and I have installed the
I can
okay.
load till 5 MVA active power, or I can load till 5 MVA reactive power.
Sorry, sir, your voice not clear.
So we can load either 5 MVA active power, or we can
Okay.
load either 5 MVA or reactive power. Any loading we can do on the same transformer.
So both the load we can add, sir. 5 MVA active power, 5 MVA reactive power.
Both not. No.
Both cannot.
E-
So
either,
solar in
either,
so solar case it will be in a different, no, sir.
either you load the
Because
either you load the MVR. If you are increasing the MVR, then MVA is going to decrease.
so,
Either you take the MVA rating, or either you take the MVR rating.
so example I'm telling, sir, so if the 5 MVA transformer is there, I have installed 5 megawatt solar plant in this transformer. So the active power is reduced now. So how can I manage the reactive power? Shall I install parallelly the SVG 5 MVA?
Do not mix two different cases. Your case is solar. His case is static war generator.
Okay.
Okay. In your case, it is a different case. If you need to compensate the reactive power, in that case, need to install a capacitor bank.
Okay. So there is any criteria to match 5 MA transformers? How much
Come on that
reactive power?
when I will come on the capacitor bank sizing, at that moment we will do simulations, and then we will decide the capacitor bank sizing.
Okay, okay, sir. Okay, sir.
You hold on, we have a topic on that. Okay, Krishna.
Okay, sir.
Okay. Yeah. Any other point? Okay, so if no any doubts, so we wind up for today. Okay, thank you. Thanks all for joining.
Thank you, sir.
Thank you, sir.
Thank you.